My name is Terrence Barkin. I'm the Executive Director of the Graphene Council, and we're hosting today's webinar series on graphene and energy storage devices, including batteries and supercapacitors and all those different chemistries that are working on in this sector. We are going to go to Hugh Glass from Paragraf, and we're going to take another look at this technology from a different perspective, and that is in monitoring the performance of these cells through sensor technology, which Paragraf excels at. So Hugh, please go ahead and introduce yourself, Paragraf, and I'm really excited to hear this because it's a different take. A lot of our presentations focus on the materials and the chemistry, and I think you guys are bringing a different angle and capability to this discussion that's really important. So let's hear what you have to say.
Brilliant. Yeah, thanks a lot. And thanks for giving us the opportunity to talk today. It's great to be here with the Graphene Council and talk to a wide variety of different people in the sort of wider graphene community. As Terrence said, so my name's Hugh and I'm the scientist and technology owner at Paragraf. This talk is going to be a bit different to the others that we've had so far because we're not producing graphene for use in energy storage devices, but instead we're using graphene to explore processes occurring within the cell. So we're producing sensors that can directly measure current in a cell or in a module, with the aim that if we can understand what's happening and sort of where the failures are, then we can optimize the cells and modules to increase efficiency. So I'll give you a brief introduction to who we are. So Paragraf are a spin out from the materials department at the University of Cambridge. We're now about 4 years old. In fact, I think officially it's our 4-year birthday next week. And we have a R&D and production facility just north of Cambridge in the UK. So here we've got around 70 people on site, and we do both R&D and production, as well as having some commercial representation. But we also have representation in the US and Japan so that we can start to expand into those markets. So Paragraf, as a company, we're a device manufacturer. So we grow graphene, but we also process it into full devices on site. The method that we use for growing graphene allows us to deposit directly onto wafers. So these are semiconductor compatible wafers, sort of the standard materials you would see with sort of normal silicon fabs. But we do this without a catalyst so that we can use standard semiconductor tools to produce devices. So because we can use standard tools, we can get to large scales and sort of volume manufacturing. It's perfectly achievable. So we get graphene across a whole wafer coverage, and then we can use these standard tools to pattern the graphene, put down electrical contacts, dice up the graphene, and then package them into final devices. So here's an example of what a final device looks like. So this is a standard off-the-shelf LCC20 chip carrier, and inside there we'd have our graphene device, which is then electrically contacted, so we can use it to the outside world. So our aim is to produce electronic devices at commercial scale. So there are lots of potential applications for graphene. We've heard about quite a few of them today, and I think over the next couple of months, the Graphene Council is doing some other webinars on sort of myriad of different things that graphene could be brilliant for. We're focusing on three different areas. The first of which is a graphene Hall sensor, which will be the focus of today's talk and is our most mature product. A Hall sensor is a magnetic sensor, so useful where understanding a magnetic field for an application would help improve it. So things like MRI field mapping and accelerator field mapping. So these are applications where if you understand what the magnetic field looks like, you can give, in the case of MRI, better patient care because you get better image qualities. Or in the case of accelerators, you can do better scientific experiments because you understand your equipment better. But it can also be used for current sensing, and that's what we're going to talk a lot about today. And with the robustness of graphene, battery field cell matting and current sensing is only going to become a bigger market and a bigger application need as electric vehicles become more prevalent. Some other applications we're looking into are graphene biosensors. It's not as mature through our R&D at the moment. Hall sensors, we have products which are for sale at the moment. Biosensors still in the R&D stage, and maybe around a year away before we get to sort of the product stage, but something that we're spending a lot of time thinking about. And then again, sort of slightly further back in the R&D chain is the graphene solid state devices. So this is sort of the holy grail of graphene devices, and it's something that we're working on, but is sort of a lot of R&D still to go to be able to produce that at scale with the quality that's required. But it's something we're confident that we can achieve. So now to get into the meat of the presentation and how this relates to energy storage. So this is the graphene Hall sensor, and it's a magnetic sensor that we're producing on site. So a Hall effect sensor is a magnetic sensor. Graphene is the active material in this device. It's typically a cross shape, so you would have a cross of graphene through which current flows. And then as a magnetic field is exposed to that device, a voltage is produced perpendicular to it. So we get a direct voltage measurement which is proportional to the size of that magnetic field. So we can use that to map magnets such as the MRI or accelerator applications I mentioned, but crucially we can also measure currents, as when a current flows through a device, it produces a magnetic field, and we can pick up that magnetic field that's directly proportional to the amount of current flowing through the device. Graphene is particularly suited for these devices, and you'll see lots of literature on graphene Hall sensors, and that's because of the tunable and low carrier concentration coupled with its high mobility. So this gives us a really high signal to noise ratio, so it can be much more accurate than standard silicon Hall sensors. The robustness of graphene is also really useful, as the sensors can be used in extreme environments where other sensor techniques just won't work. And we don't see any hysteresis, even at really high magnetic fields. So you can use just one sensor type for many different applications. So this uses quite a few of the sort of real benefits of graphene. Another key feature of graphene that we're all aware of is the fact that it's a two-dimensional material. And in sensing applications, this is a massive benefit, as it means you really are only measuring signals in the direction of the graphene plane. In standard electronics, such as silicon, there is a depth to the sensors, and that might only be tens or hundreds of micrometers, but it's enough to produce spurious signals that reduce accuracy, or they could require expensive shielding to counteract them. So we've actually measured this effect in graphene and compared it to silicon sensors, and we've shown that graphene has at least 2 orders of magnitude smaller errors due to this planar effect than you would see in silicon sensors. So it's really utilizing that two-dimensional nature of graphene. So how does this all apply to batteries? So in energy storage, we've been working with a couple of partners to collect this data. This work was done in collaboration with Danica, who are a battery engineering specialist, and the Warwick Manufacturing Group, who have been mentioned a few times already today and are clearly key players in battery research. So what we're showing here is taking graphene magnetic sensors. You can see these are the graphene chips mounted into a little PCB for taking these signals out. And we're mounting them directly onto a pouch cell or onto the bus bars that feed into the cells and directly measuring the current flowing within them. As it's a non-contact measurement, the graphene sensors are literally just placed on top of the cell. They don't need to be built into the system. It doesn't disrupt the current that's flowing in the cell. So the tests and the use of the battery can proceed as normal, and we're just measuring what's happening within the cell. So that means that we get a true reflection of what's happening during use, during charge and discharge, be it at the cell level, pack level, or module level. What we're measuring is the current. The graphene doesn't mind what the current is flowing in, so you could place the sensors in any current carrying component, which means that you need fewer different technologies in a sort of a battery management system, and they can slot into any current test setups that you already have. For example, here we have 8 sensors distributed around a pouch cell, and that means that we can see how the current is distributed at different points of the cell. But you could also place them on the current tabs, or as we're shown here with a lot of Kapton tape to hold them in place, you could mount them onto the bus bars actually flowing into and out of the cell, so you can measure any current fluctuations either side of the cell or across different cells in a pack. And finally, there's no crosstalk between the sensors. So they can be packed very densely to give high spatial resolutions. Here we've got 8 on the pouch cell, but you can imagine making an array of sensors over a cell to really finely map the current density and see how that changes during charge and discharge. So it's not just an idea we've had, we've actually shown that this can work, and we've been exploring all the possible benefits that this technology could have sort of in battery R&D and in manufacture. So here we worked with Danica, who are a specialist battery engineering company, to show that we can directly measure the current flowing into a pouch cell and not have to rely on temperature changes as a proxy for that current density. We get a real in operando measurement of the current. So a graphene Hall sensor was mounted directly in the center of the pouch shell, and we discharge that cell with progressively increasing currents. And as you can see, there are clear peaks when the discharge starts, and this corresponds to more current flowing through the cell, produces a magnetic field, and that's what we're picking up in the graphene. We can sense that magnetic field. We get this nice flat profile as there's a constant discharge, and then as soon as the discharge is turned off, we see the decrease in current. So we're getting a real snapshot of what's happening, and this is exactly what you would expect for a discharge profile. And then as we increase the current from 10 amps to 25 amps, we see a corresponding increase in the size of the signal, so proportional to the signal that we're putting in. So we're linking this back from what the signal we're seeing in the graphene to what's happening into the center of the cells. Linking this back to the sort of robustness that we were saying about the graphene is that you can't oversaturate this sensor. You'll just keep getting higher and higher signals, and you'll be limited by whatever electronics you're trying to pick them up. You're not going to damage the graphene. So that means that if you're looking for failure analysis, you'd be able to pick up any large current spikes without affecting the sensor, and then you could go back to using it as normal afterwards. So this was a really nice proof of principle that what we expected to happen could happen, and we're looking forward to working with more people to prove and see how this can be useful in test setups. We've done similar tests with the Warwick Manufacturing Group. These are in a little bit more detail, and we've shown that the graphene sensor can distinguish between charge and discharge. So not only are we sensitive to the magnitude of the current in a cell, but also to the direction that it's flowing in. So this is particularly useful for mapping how the current flows through the cell, and you could use it to improve the architecture of a cell to make sure that all of the electrode material is being used. So here we've got sensors distributed around a cell, and you can imagine comparing how much current is reaching the bottom of the edges of the cell to the center, and redoing the layers, doing the architecture of the layers to make sure you're utilizing every bit of material in that cell. So here we've got the difference between the charge and the discharge. You'll see on this figure increasing amounts of discharge with increasing signal, as you'd expect. And then as we switch to charge, you see an opposite sign, meaning that we really are sensitive to the direction of that current flow. That's in contrast to the often used temperature measurement, where thermal changes in a cell are used as a proxy for current density. Those measurements don't distinguish between charge and discharge, and there's a thermal lag, so you don't get a true understanding of the current flow mechanism. So final piece of data, which was also collected at WMG. Here we're looking at how quickly we can collect data, which is particularly important for failure analysis or improving the efficiency of a battery management system. If your battery management system is trying to make decisions on where to distribute current, it wants that information as quickly as possible so it can respond and give the best efficiency and safety of the cell. So here we applied a discharge for a 10-second pulse, and saw a really nice discharge step, which is exactly what you would expect. And there's no lag between the switch on of the discharge and the acquisition of the signal. So it's worth noting that this is also electronics acquisition limited. We collected 90 data points in 10 seconds, so we can get lots of resolution on that current. But graphene itself can work at much higher bandwidths. So if we worked on in the future and needed higher bandwidths, that would be possible. It would involve tweaking some of the electronics. But it's safe to say that the Graphene Hall sensor is giving a true snapshot of the current distribution at any point in time. So we think this is going to be really useful for failure analysis, particularly, and also optimizing the architectures. So that's an overview of what we've already shown is possible with these sensors, but we have lots more development going on just on the Hall sensor. And we're continuing to work with WMG to really understand how this could be integrated into battery management systems. At the moment, the devices are quite large. They're a few millimeters across, but because we're using standard production techniques, we can scale this down pretty easily. And that's one of our main development programs at the moment. We're aiming to shrink the devices down to just a few hundred microns, which would massively decrease costs and allow very high spatial resolutions for mapping. So that's kind of an overview of where we are at the moment. We can see lots of possible uses for this in battery use cases, and we're talking to quite a few different people at the moment. So I mentioned Danica and WMG today, but we're also talking to quite a few others as well. I won't go through these full lists, but from sort of an R&D point of view, we think the main benefits will be from really understanding what those failure mechanisms and aging mechanisms are, being able to predict failures or optimize out sort of energy efficiencies in those cells. And that's both within a cell or a sort of multiple cells put into a modular pack, where you could see how different different cells are drawing current within that pack and redistributing the current based on that information. This could also be used as in-service health monitoring. So not just at the R&D stage, but actually while they're being used to monitor for early signs of aging and hotspot formation. And that could improve lifetimes of cells and their safety, which is obviously going to be critical. And finally, also at the end of life, when the batteries are no longer suitable for electric vehicles, we want to be able to reuse them and we want to reduce waste. So being able to rapidly screen batteries for failure points and hotspots and grading batteries is going to be an important market to come. So to help people get started with these and to help understand what these sensors can do, we've got this sort of standard set up. As I say, the Hall sensors are available now, and we've been working with partners already, and we have an electronic sort of plug and play box, which allows quick analysis and plug into a standard test system to show how these can help in battery R&D. But we also have the ability and the in-house expertise to provide technical expertise for improvements in how this could be integrated into current battery management systems. So finally, we think this is a really interesting and potentially important development in battery test equipment. So we'd love to hear from any battery researchers, manufacturers, recyclers, to discuss the possibilities of this technology and how we might be able to work together to produce a new test system. So thank you very much for listening, and happy to take some questions.
Well, Q, this is Terrence. Thank you so much for that. That's really, really, really interesting. And I think there's just an unlimited horizon of where this technology could be used. If you want to stop the screen share, then we'll go to Q&A.
Yeah.
I'm quite sure that Dexter might have a few questions for you. I know from our audience we have questions. The first one that comes to my mind is you mentioned a couple of times that the current technology is using thermal measurements as a proxy for current flow. Is that the state of the art for this kind of diagnostic, or who are you replacing with this new approach?
Yeah, so there's actually a few different ways that you can do this currently. Temperature measurement is the main one for in use. Because you can place them on the top of a pouch cell. It's an indirect measurement, doesn't get in the way of the cell, but it does have thermal lag. And clearly it's not the only thing that's going to be changing temperature in a cell. So it's not a great proxy, but it works relatively well. For inline measurements in the bus bars or in other parts of the circuits, you could use more conventional current sensing. You could use shunt resistors, you could use the ring-based current sensors that you often see. Those are good and they work, but what we think we can bring is more accuracy to those measurements and not have to be built into the circuit, so that if there's a failure in the sensor, it doesn't affect the battery. So we want to be separate from that, but providing the same level of detail.
So another idea that comes to mind, obviously, is that these sensors, I think the in-use monitoring and load balancing and health monitoring also could be systems control, monitoring the signals and use it for systems control. There just seem to be so many ways that these sensors could be superior to existing technologies. The question with all the new technologies, one is, does it work? Second, how do you displace, an entrenched supplier? And even if you build, the better mousetrap, it has to compete on cost. So where do you guys come in on cost?
Yeah, so as it cost is very directly linked to scale. It is a commercial discussion. Because we're using these standard techniques, we can scale up, and we think we're going to be very competitive with other sensor techniques which give sort of similar performance, or even better on cost but giving better performance. Now, for things where applications like the inoperando measurements of a pouch cell, there currently really isn't anything we're replacing. So that would be a new technology. But for current sensing for, say, electric vehicle charging, there we're going to need to compete on cost to some of the high power applications. But with the scales that we can get to, we're pretty sure we can be competitive.
Understood. And Dexter, what's your take on this?
So I guess just to sort of clarify, so you can use this for lab testing and measurement. You could potentially use it as a quality control in manufacturing, and it could be even used in operational settings where you need to measure the what's happening to the battery. So sort of the whole lifespan, and you mentioned even when the batteries are ready to be retired, you can see whether they're can be renewed in some way. So the whole life cycle of the battery, that these sensors could find application.
Exactly. I think understanding what's happening within a cell is important at every stage of a battery's life, whether it's quality control for them to first pass, or understanding why they failed or if they're going to fail at the end of their life.
And Hall effect sensors have never been used in this area before. This would be graphene or otherwise.
They've tried. So there are a couple of papers from, I think, the late 80s where they've tried to use silicon Hall sensors, but the resolution isn't there. They're just not good enough in accuracy and resolution, and that's where graphene comes in. You get an order of magnitude, 2 orders of magnitude better accuracy, and suddenly you can pick out these currents which you couldn't see with conventional Hall sensors.
I just want to.
So it's not it's definitely a case of where graphene is allowing us to do something that people have tried before.
Okay, I wanted to make that clear that you couldn't just decide to use any Hall effect sensor. You needed these graphene Hall effect sensors because of sensitivity and
sensitivity and robustness to magnetic fields. Something I didn't talk a huge amount about here is the wide range of fields that graphene can handle, because there's no magnetic components and it's really, really robust and the high mobilities. We've been working with the high field magnet labs in the Netherlands, and we've taken these sensors all the way up to 30 Tesla, which is one of the largest fields in the world. It takes about 1 Tesla for those big magnets to pick up cars. We've got to 30 Tesla, and we don't see any hysteresis. So, there aren't any other Hall sensors that can sort of achieve that kind of field and over those temperature ranges. So
these have been tested in CERN, right?
Yes.
Right.
Yeah, so we worked with the magnet group there to look at how accurately we could map a magnetic field. And that's where we measured the planar Hall effect, so we could see the true two-dimensional layer.
And how would you describe the level of sensitivity and also the speed of signal that you get? I mean, we know it's exceptionally high, but how would you describe it to someone?
Yeah, so I guess I would say we're an order of magnitude better than conventional silicon sensors for sort of similar applications. Sorry, what was the second part of the question?
Well, it was the speed of signal, right? So you don't have the lag, right? So real time measure. So the holy grail, of course, is real time measurement and extreme high sensitivity. And I thought sorry to interrupt you, Hugh, but the other thing I thought that was fascinating from your presentation was the ability of the sensor to make a differentiation between discharge and charging.
Yeah, exactly. And I think if we're comparing the resolution to other current density measurements in batteries, there isn't really anything good to compare it to, because temperature is not a direct measurement of that current density. So if you want to look at the sort of the accuracy of distinguishing between charge and discharge, you get the direction of the current flow as well. There isn't really a comparison to make, because you can't do it directly on top of a battery cell with current applications. For on the bus bars and on the circuits where there are competing technologies, then we come into the sort of order of magnitude better resolution than silicon, and more robust. You can use one sensor for different applications, but there is a competing mechanism there. So I think being able to produce a current density map that's not just magnitude but also direction helps really understand these processes that are happening in a cell, because they're complex things, multiple layers of electrodes. Figuring out exactly what's happening is not an easy task.
Yeah, that could dramatically alter the development of batteries in general. Having that information.
Yeah.
One could argue comparatively, everybody's been flying blind. I mean, if you think about this ability to monitor with a much higher degree of specificity, speed, and accuracy, I think it really begs the question. And this is not us trying to pump up Paragraf, but the question is, why would not every single battery lab everywhere use these wherever they can, just so you have more detail on what you're actually producing in real time? It seems like that this could have a really significant impact in the ability to measure and real-time monitor quality control, performance, in use, et cetera, as Dexter commented on.
Yeah, certainly. I mean, that's what we're hoping, and we're trying to work with as many partners as possible to prove what information we can get from this and prove its usefulness.
There's an interesting question, I think, from the audience, and that is this would be an operational question. Is it possible to detect dendrite formation in lithium-ion batteries?
Yeah, that's a good question, and one that we've thought about a bit. It technically should be, because you would get current density changes at those points, and the current flow would be different. It's not something we have directly measured yet, but as you can see from the data, we're just starting out on this journey of proving what we can do. But if the current density is changing in that part of the cell, then we would see a change in the magnetic field.
Right. So it's just a matter of collecting the data and seeing where the dendrite.
Exactly.
Right.
It would take some initial research of like making sure we've got dendrite formation, seeing what that looks like in the sensor signal, and then using that to sort of feedback.
Excellent. Thanks.
Excellent. Well, there is one last question on there, just asking about the amount of graphene that's used. But I think this is I want to hear you say it. This is what makes graphene so amazing. How many atoms of carbon are there in one of these sensors?
So we've got a chip of graphene inside those chip carriers, and it is monolayer graphene. So we're just using a single monolayer of graphene as the active material. So if you think whatever about 1 mil by a monolayer is in terms of number of atoms.
Yeah. It's incredibly impressive, and the survivability of the material also speaks to the longevity, right? So you basically will not destroy it in use. So I think that's another business case compared to some of the other sensor technology, is the longevity of the sensors that you're providing.
Yeah, certainly.
So with that, Hugh, I want to say thank you to Paragraf, of course, for being a member in the Graphene Council. Congratulations on the amazing technology you guys are developing, not just for batteries, of course, but as we've seen in other settings with the biosensors and in general with your sensor technology. It's critically important for all things that as we go forward. The ability to measure and monitor is critical to better performance for all systems. And so I want to thank you for taking the time to share that with us today. Thank you.
Yeah, thanks a lot. Thanks for having us. And if anyone, any other participants have anything they want to ask or collaborations to do, then just get in touch.
Excellent. We will share your slides, and there will be recordings of all the sessions that you've seen today. So thank you, Hugh.